Dear students, a very happy morning to all of you, and I welcome you for this session of online learning. Children, we started with light lesson. Under light, we have studied about spherical mirrors. The spherical mirrors we have seen, they are of two types, convex and concave. And next to it, we have seen the important definitions in the spherical mirrors, the two with concave mirrors. So we have seen the definitions like pole, radius of curvature, center of curvature, focal length, etc. etc. And further to that, we had a discussion on how to draw the ray diagram for a concave mirror with different object positions, and the rules for drawing the ray diagram also we have discussed. Now in today's class we are going to discuss about the next mirror, that is convex mirror, the image formed by the convex mirror, and after that we are going to see the applications of the image formation. That is a very important topic where questions are frequently asked in the board, and that carries very important. And next to that, we are going to see about the uses of convex and concave mirror, and lastly we are going to see about the mirror formula and magnification formula. And these formulas are very important in solving problems. And lastly, we are going to take up with Cartesian sign, which is very important, because these criteria determines the positive sign and negative sign for the numbers which you get in the problems in the exams. Therefore, you have to listen to it very carefully and get known the things. So let us begin the class with for the convex lens first, then further we will go into that. Children, please listen to this video very carefully and understand things. Okay children, come, we will go. Children, what you find in this diagram is a convex mirror. What is a convex mirror? A convex mirror is the one which has the reflecting surface outside and the polished surface inside. So when you see this diagram, you find the ash color shading which represents the coated side, non-reflecting side. And here the object AB is kept at infinity. When the object AB is kept at infinity, parallel rays to the principal axis strikes the mirror, and as soon as they strike the mirror, they get reflected in the reflecting part only. So you see the reflected rays which are bending with that angle, and see to the arrow marks, and extend the rays which are reflected. Obviously they fall on the point F, which is principal focus. So when an image is kept at infinity in front of a convex mirror, you get the image at the focus on the other side of the mirror. So the image size is very pointed. Okay, so when the object is kept at infinity, you get the image at F, and it is a highly diminished, we say it is a highly diminished image, and since it is formed on the right side, it is virtual, and you get an erect image. So these are the qualities of the image we get when the object is at infinity. Now this is the second position where the object is being kept. and the position of the object, which you see as an upward arrow above the principal axis, and this is being kept between the infinity and pole. So between infinity and pole, the object is being placed. Now trace the rays according to the laws which we had seen. Now draw a parallel ray. So a parallel ray that is parallel to the principal axis, after reflection it gets reflected and the extension of the reflected ray will pass through the principal focus. So there we complete the first ray diagram. The second ray diagram is to connect the height of the object with the point C, which is called as center of curvature. As we have seen before, any ray which passes through center of curvature is reflected back in the same path, and that's why you see two arrows in the opposite direction. One is the incident ray and the other one, which is in the opposite, is the reflected ray. So where do these two rays meet up? They meet up at a point just closer to the non-reflecting surface of the mirror, and that is being shown as a green color arrow mark, which is an upward arrow mark. So here is the image formed. So when the object is being placed between infinity and pole, the image is formed behind the mirror. And what is the quality of the image formed here? It is upright, and since it is formed on the right side, it is virtual, and compare the height, it is diminished. So the properties of the image is diminished, virtual and upright. So this is a very important diagram which is being asked in the board examination. Children, by that ray diagram, we complete the ray diagram for the spherical mirrors. So in the first class, we have seen and we have drawn 6 image formation for a concave mirror, and today only 2 positions for a convex mirror. So totally 8 diagrams, 6 for concave and 2 for convex mirrors. With that, we are completing the ray diagram process. Now we will apply those knowledge, the image formed by the concave mirror and convex mirror, in its applications. The applications of the spherical mirrors with the image formation is very, very important, and this is a very important topic as far as the board questions are being concerned. Now first let us take up the rear view mirror of the cars. Now we find the rear view mirrors wherever we have a vehicle. For example, if you take your motorbikes or the scooters or the cars, it is being fitted with a mirror which is called as rear view mirror. What type of mirror is that? It is purely convex mirror. And why convex mirrors are being used for the rear view mirrors? And it's a very, very important board-based question. Now the image formation that you have seen just before this slide is the application of the rear view mirror. That is, for in front of a convex mirror, the object is kept between the pole and infinity. So what do you find? Where is the image formed? You see the image formed is A dash B dash, which is on the other side of the mirror, and it is virtual, diminished and erect. So these properties makes the convex mirror to be an rear view mirror for automobiles. So convex mirrors are used as rear view mirrors in vehicles. It is due to the reason that convex mirrors produce an erect image of the object, and the image formed in the convex mirror is much smaller size than the object, due to which the driver is able to see large area behind him and drive carefully. So in the mirror, the field of view is wider field of view is seen in the mirror. because of this property, and because it gives an erect object. Because of this property also, the convex mirrors are being chosen as rear view mirrors. Now you can see in the mirror, the car which comes behind, it is seen upright, and you can see also some 3 cars which are following one by one. So it gives a wider field of view, as well as it gives an erect image, and that's why convex mirrors are used for rear view mirrors. This is the next application of the spherical mirrors. The mirrors used for shaving, and it used by the dentist. Both are similar. And what type of mirror is this? Obviously, this is concave mirror, because for shaving as well as the mirror used by the dentist to examine the teeth, the image should be enlarged. We need an enlarged image for seeing our face as well as for the doctor to see the teeth. So a concave mirror is being used. And where should the object be placed? Look at the ray diagram here. When the object AB is kept in between the pole and the focus, then it gives the image A dash B dash, which is on the right side of the mirror. That means the virtual image. And compare AB with A dash B dash, it is enlarged. So this ray diagram, when the object is kept between F and P, is purely an application of the shaving mirror and dentist mirror. So when the questions from the Cbse board is being asked about these type of mirrors, this ray diagram you must be able to draw in the exam. So dentists use concave mirrors to see enlarged image of the teeth for examining it. If the object is placed close to the concave mirror, it forms an erect and enlarged image of the object. So the dentist holds the mirror in such a way that the tooth lies within its focus. So the ray diagram is very important in connection with the shaving mirror and the dentist mirror. Now here is the next application of the spherical mirrors. What you see in the slide is a solar cooker and headlight of a car. The solar cooker uses the solar energy to cook the food. Now you can see the cooker is being kept on the focus of the concave mirror. So you see to the ray diagram here. Parallel rays to the principal axis. After reflection, they pass through principal focus. This concept, where the parallel rays meet at the point principal focus, is being used both in solar cooker as well as headlight of the cars. Now let us see one by one. Now let us see the solar cooker. This solar cooker is placed at the point F. So what happens is, when the sun rays, when they are parallel to the concave mirror, all these rays will converge at the point F where the solar cooker is being kept. So the temperature becomes high due to the converging of all the reflected rays here. So enormous heat energy is produced at this point F, and so the food is being cooked here. And exactly opposite of this is the headlight of the cars. The headlight of the car is kept at F, and when the bulb glows, now in the diagram you have to take the opposite direction of the arrow marks. When the bulb is at F, then it illuminates, it gives light, and it touches the surface of the mirror. So when it touches the surface of the mirror, it gets reflected, and the parallel beams of light are being ejected on the street. So you have to just opposite the arrow mark. The bulb is kept at F. When it gives light, these light rays are falling on the surface of the concave mirror, and since it is emerging from F, these reflected rays are parallel, and these parallel rays are falling on the street, which enables a driver to see the road clearly. So these are the two applications of the concave mirror where the object is being kept at F. So let us read the slide. Concave mirror is used in a solar furnace or solar cooker, whatever it is. The solar furnace is kept at the focus of the large concave reflectors. The concave reflector focuses the sunlight heat on the furnace and the high temperature is achieved at F. Then concave mirror is used in the headlight of vehicles as reflectors. When the bulb is placed at the focus of the concave mirror, then it produces powerful beam of parallel rays by which we can see things even in the dark. So these are the two applications when the object is kept at F of a concave mirror. So this is also an important question as far as the Cbse exams are concerned. Now let us pass on to the uses of concave mirror. Concave mirrors are used in torches, searchlight and LED headlights of vehicles to get parallel beams of light. So just in the previous slide we have seen when the object is kept at F, after reflection it renders parallel rays to the principal axis. So this is the application where the instruments like torches, searchlight and headlight of cars are being used. The second point is they are used as shaving mirrors to see large image of the face. They are used by dentists to see large images of the teeth. And lastly, large concave mirrors are used to concentrate sunlight to produce heat in a solar furnace. Therefore, there are totally 4 applications in a concave mirror. So this is also a frequently asked board question. This slide gives you the uses of convex mirror. The most important use of a convex mirror is it is used as a rear view mirror for vehicles. So why it is being used? Because it gives an erect image, also a wider field of view. You can see in this mirror a large number of objects are being seen in the mirror. So because of these two properties it is used as the rear view mirrors, and it is also used as security mirrors. You would have seen in some jewelry shops and where there is a blind turn on the hills, you can see this mirror where the driver can able to see the reflected image when he is not able to see the road actually, and thus he can drive the vehicle safely. That is why it is called security mirrors. So these are the 2 applications of convex mirrors. Children, this slide is a very important slide, and whatever I tell you now, you should listen very carefully. This slide gives you the mirror formula. Now look at this ray diagram. This ray diagram you would have already drawn, and for a concave mirror, see to the object. Where is the object being kept? The object is being kept at a point A. Where is the point A? It is in between C and F. So the object is in between center of curvature and the focus. So according to the ray diagram rules, if you draw the 2 rays, the intersection of the 2 rays is being formed at the point B where the image is being obtained. So A is the point where the object is there, and B is the point where the image is being obtained after the ray diagram. Now look at the letter U. So there is an arrow mark above the object. So the starting and the ending, the distance AP. that distance is kept by the letter u, and this is the object distance. So object distance is the distance from the object till the pole of the mirror. So AP is the object distance, and always this object distance is kept by the letter u. Now similarly, the image distance. Where is the image formed? At the point B. So from the point B, measure till the point P, that is the pole of the mirror. That distance is the image distance. So the distance BP is kept by the letter V. And you know that about the focal length, which we have seen. Focal length is the distance between focus and the pole of the mirror, and we keep it by the letter F. So the three letters U, V and F are very important here. U is the object distance, V is the image distance, and F is the focal length. So these three distances you must bear it in mind. Now there exists a relation between these three relations. The formula is 1 by F is equal to 1 by V plus 1 by U, where F is focal length, V is image distance, and U is object distance. And this is known as mirror formula. So in a mirror formula, 1 by F is equal to 1 by V plus 1 by V. So the values of U, V will change according to the position of the object where you keep. So in that case, those distance may be small or big. Okay? Children, this is another important slide which gives you the relation for linear magnification. Linear magnification is kept by the letter small m. What do you mean by magnification? Magnification is the amount of enlargement or the amount of diminishment of an image. In some of the image formations, we see enlarged image, and some of the images are diminished. How much is the enlargement or how much is the diminishment? This is being given by the term magnification. So for magnification, you just recall the same diagram which we have done before. Now the height of the object, let the height of the object be HO, as I have indicated. And now he see the height of the image, HI. So when you compare height of the object and height of the image, you see in the ray diagram that the height of the image is magnified, or it is more in height than the object. So it is a enlarged image. Okay. So in whether it is enlarged or diminished, the magnification is given by two important formulas. The first formula is height of the image divided by height of the object. A very important relation, and I tell you now, it seems to be simpler, but at the time of examination, I have seen many students, when they write this formula, they get a doubt whether it is it the height of the object by image, or is it the height of the image by object. So there exists a doubt. So get clear, it is the height of the image divided by height of the object. And we have another formula for magnification. It is by minus V by U. The symbol minus is very, very important. If you leave minus, you will land in difficulty. So this minus is very important. So linear magnification has two formulas. One is Hi by Ho, height of the image by height of the object, and the next one is minus V by U. And you know that what is V? It is image distance, and you know U is the object distance, and that's why I have indicated the minus sign in red. It is very, very important. So M is equal to Hi by Ho, which is again equal to minus V by U. Important relation which we often use it for solving the problems. Children, this is the most important slide of all the slides. So listen to me carefully. It's very easy provided you know the concept. Otherwise, mugging up will not help you. So first look into the diagrams which I had given to you. I had given you two diagrams. The one is the mirror with the mirror, and the other on the right you find the graph. Right? Now you just go to the mirror diagram. This is the usual one which we know already. You have a concave mirror. P is the pole of the mirror, and then a principal axis is there. Red color object is there upward, and yellow color image is there downward. And as we have seen before, the object distance is there and image distance is there as there. And so this is the representation for the diagram. Now you have some plus and minus, that we will come to it later. Now there is a graph on the right side. So this is an ordinary graph which you are using it since you are in class 6. So the graph is divided into 4 quadrants, and O is the origin. On x-axis you have left side negative values, right side positive values. Similarly in the y-axis, above the origin you have positive values, and below the origin you have negative values. So once when you are clear with this graphical symbols where the positive and negative comes, the same thing you can apply it on the mirror which is on the left side. Okay, so fix the origin of the graph. Listen to me very carefully. Fix the origin of the graph on the point P, that is the pole of the mirror. Okay, so O should be fixed with the point P. Then any distance which you measure on the left side of P, it is negative, right? And any distance which you measure on the right side of P is positive according to the graph. Okay, and any distance which you measure upward of the principal axis, it is plus. And any distance which you measure down of P, it is negative. That's all, children. This is the simple concept that you have to understand. So you have an imagination where the origin is being pasted on the point P of the mirror. All left side distance will be negative. All the right side distance will be positive. All the upward distance are positive and all the downward distance are negative. That is what it is given here in the diagram. You see some positive and negatives there, and it will certainly go with the rule what I have told you. Now read the slide. The object is always placed on the left of the mirror, and the light from the object falls from the left to right, isn't it? Then all the distance parallel to the principal axis are measured from the pole. So all the distance are measured from the pole. All the distance measured to the right of the pole are positive. Okay, now you can correlate the graph. All the distance measured to the right of the pole are taken as positive. Or else even you can take the pole P and fix it on the origin O. In this way also you can calculate. The next one, all distance measured to the left of the pole are taken as negative. The height measured upward perpendicular to the principal axis is positive. the height measured downward perpendicular to the principal axis is taken as negative. So this positive and negative becomes easy when you compare it with your ordinary graph. Okay. This is the same slide as you had seen in the previous. There it is diminished, here it is enlarged. That's it. Now here you don't find the graph, so you have to fix the graph imaginarily where the origin coincides with P. Now you see to the distance. So distance on the left side of P, that is the object distance, it is taken as negative. So distance towards left, you can see a mark and it is being taken as negative. And on the right side of the P, you see distance towards the right, they are to be taken as positive. And you see the principal axis, you find an upward red color line. So distance which are above the principal axis are measured positive, and the distance which are down the principal axis, they are measured as negative. So this is a very important concept, and the sign is very important when you do the problems, and when a small mistake in the symbols with the minus, if you take it as plus, then everything will go wrong. That's why this is the basic for the sign conversion, and you must be well aware of it. Children, we are going to apply the sign conversion in the ray diagram shown here. Now examine the ray diagram here. It is the usual diagram for a concave mirror. The object is kept between F and C. So, and after the reflection, by observing the rules of the ray diagram, you get the image, inverted image, and it is being represented as orange line. Right? Now you see to the measurements. Now above the object you have a distance u equal to 25. That means the object distance, we have already seen, the object distance is the distance from the object till the pole of the mirror, and that is 25, it is given here. And the distance between the object and the image, it is given as again 25 centimeters. Now when you come down, the distance between the image and the pole of the mirror, it is kept by the letter V, that is image distance, and it is being kept by 50 centimeters. Now focal length is the length between the focus and the pole, and that is being given as 50 by 3 centimeter. How this 50 by 3 centimeter comes, we will discuss later. Now just remember, it is 50 by 3, which is equal to 16.6 centimeter. Now we have to apply the Cartesian rule here, that is the sign conversion here. Now you may observe, when you fix the graph origin on the point P, all this distance, irrespective of all this distance u, v and f, lies on the left side of the origin. So this left side of the origin, they indicate what sign? They indicate negative sign. Therefore u, it is not 25, it is minus 25. V, it is not 50, it is minus 50. F is also, the distance lies left side of the mirror. Therefore it is also minus 16.6 centimeter. So you recall the ray diagram which you have drawn before. You have drawn 6 ray diagrams. Out of these 6 ray diagrams, all the first 5 ray diagrams gives you the real image, The real image is formed on the left side of the diagram, left side of the mirror. So, for all these 5 diagrams, where it forms a real image, U, V and F, all of them are negative. And only one position, this concave mirror, forms a virtual image. Where is the virtual image formed in a concave mirror? Can you recall it? Yes, when you keep the object between F and P. When you keep the object between F and P, you get the virtual image on the right side of the mirror. Just you go and check the diagram. So you get the image on the right side of the mirror. So when it is on the right side of the mirror, then the image distance V becomes positive. That's why you see I have given you here V is positive for virtual. And all the other distance, that is U and F, they lie in the left side. So to sum up, so for all the out of the 6 ray diagrams, the first 5 ray diagrams, you get only real image. What is a real image? When the image is formed on the left side of the mirror, it is a real image. So when the image is formed on the left side, U, V, F, all these 3 lies on the left side of the pole of the mirror. Therefore, they are taken as negative. And only for one position, the concave mirror gives the virtual image. That is for the position when the object is kept between F and P. So you get the image on the right side of the mirror. So when the image is on the right side, the image distance becomes positive. And the remaining 2, U and V, remains the same, negative. So bear this in mind and repeatedly listen to this slide, how we are applying the conversion sign for the diagrams. Children, let's move on to solving problems on the basic ideas which we have discussed so far. Now, to begin with, let us start with the easy questions. Now, read the question now. Suppose the height of the object is 3 cm. Height of the image is 12 cm. What is the magnification? So, when a problem is being given, you have to analyze the problem. What are the quantities given? Next, what is being asked? So this you have to write as the heading given and asked. So what is given here? One is 12 centimeter and the other one is 3 centimeter. So what is 12 centimeter? Height of the image. Height of the image, we keep the letter HI, 12. Height of the object, we keep the letter HO, 3 centimeter. Therefore, magnification has a formula, height of the image divided by height of the object. So 12 by 3, 4. What is the unit of magnification? Magnification has no unit. Why? You see to the formula, the height, the unit for height in the numerator is centimeter and the unit for height in the denominator is also centimeter. Therefore, centimeter and centimeter in the numerator and denominator cancels away and resulting in no unit. Therefore, the magnification is 4, just 4, a number. Now, let's see to another question on the same magnification. Read the question. Suppose the object distance is 3 centimeter in front of the mirror. So in front of the mirror is very important. Why? It gives this sign. What sign it gives in front of the mirror? Minus. Because we are fixing the origin with the pole. With the pole, then left side, all the readings are negative. Image distance is 12 centimeter in front of the mirror. Then it is also minus 12. Find the magnification. Now there are two numbers given, 3 and 12. So what are they? 3 is the object distance and 12 is the image distance. So object distance is kept by the letter u. So u is equal to minus 3. In the question it is given 3, but when you are writing given quantities, it has to be minus. And that's why I told you, you have to be very careful in the partition sign. Similarly, image distance, because the image is also formed in front of the mirror, then 12 becomes minus 12. Now use the formula magnification is equal to minus V by U. Now while substituting the values, you have to be very careful. Now magnification M is equal to minus, so that minus comes first, and V, what is the value of V? Minus 12. So minus of minus 12 by U. What is the value of U? Minus 3. So the numerator becomes plus 12 and the denominator becomes minus 3. So when you do the division, you get minus 4. So the magnification obtained here is minus 4. What does this magnification represents? It is the amount of enlargement or diminishment of an object. This is a very basic question. Find the focal length of a convex mirror whose radius of curvature is 32 centimeter. What is given? Radius of curvature R is given as 32. And what you are being asked to calculate? Focal length F. So you have the formula R is equal to 2F. So R is equal to 2F, where R is the radius of curvature and F is the focal length. So 32 is equal to 2F, or F is equal to radius of curvature divided by 2, 16 centimeter. So this is a very simple problem.